So today we're going to talk about GAN or Generative Adversarial Network. Let's write it out. GAN, GAN, and G stands for generative. Generative. It was originally invented to generate images of faces and was the first realistic generation of synthetic images that achieved by the neural network. It's almost like 10 years ago in 2014 by Ian Goodfellow. This is very significant because it's how generative AI for images started, that people have faith in this future and the promise of this neural network in 10 years. And that is pretty incredible how much we're able to accomplish in terms of image generation using neural network architectures. So that's where it always started. Okay, so GAN, generative adversarial networks. We're going to talk about what we mean by GAN and what does adversarial training means. All right, so let's erase the loop so we have a bit more space to work with. So what I want to start with is a very tiny GAN, very tiny generative adversarial network. So we have this generator over here. So we're gonna say generator over here. And it is a one layer network with one linear layer. And we also have a discriminator network down here. That is again also one layer. And I have both matrix representation on the left-hand side and also the graphical representation on the right-hand side. And take a look at the generator part. So the generator, I started with this noise. In fact, in this case, I want to generate a batch of I would like to generate a batch of 3 images. So I'll start with noise with, in this case, 2 dimensions. And my output, my desired output has 4 dimensions over here, 4 dimensions here. And we have a network going this way from 2 to 4. And I have 3 examples. If you looked at the equivalent graphical representation on the right, and so this kind of similar like this. So I have 2 dimensions mapped to 4 dimensions, some sort of transformation in between. And so this is a generator. And I started with 3 examples. Again, 3 noises. I would like to generate 3 synthetic or generated or fake data points. Okay, so usually we just write it down. We usually call this, we start with noise, and we'll get some kind of fake images over here. And then so this, even though they are fake, we like them to be as realistic as possible. And the naive way of training this network in the very classical supervised training sense is that you hire someone, you look at the result and say, okay, does it look like a face or not? No. And does it look like a face or not? No. And for every single input, and you do that for multiple epoch, which is not possible. You can already imagine that you just cannot sit there and provide labels all the time while you're training. So instead of having a human being to provide feedback, so the idea is that what if we can train a network to provide this feedback kind of on the fly every time the generator generates something, where this new network we call discriminator is going to just provide some feedback. And what kind of feedback can it provide? So let's say this discriminator would like to just provide a feedback in the simplest feedback is a binary feedback that is it real or not? Can you tell it is a face or not? Is it being, so this is why we have this 4-to-1 mapping in this case. Now it's discriminator that goes from 4 input to 1 because we're talking about binary output that is it real or not and going all the way down here. Okay. And then in order for discriminator to function, discriminator it cannot just like look at the fake and saying that, hey, is this fake or not? It's not, it is more effective that we also provide some actual real images. So these are where the green diamonds represent real data. So we have real data. And then by feeding the discriminator with both fake and real data, we would like the discriminator to learn how to differentiate them. And so we will be able to say, hey, this is probably the fake, this is probably real. And just generator and discriminator, we're talking about two different networks. They will be competing to trying to be better. One generator trying to fool discriminator, a discriminator trying to be able to detect the fake images as opposed to the real images. So this is really at a high level. And for the rest of the lecture, we're going to break it down what the generator does and also what the discriminator does and how we can visualize what discriminator network is actually saying. And so let's write down this D here to represent the discriminator. And well, I'm going to zoom out just a little bit so we can see this setup in kind of in a more bigger picture. So again, so we have noise on the left side, feed only to a generator, only feed generator 3 data point, and it generates 3 fake images. But we feed the discriminator with both the fake and real data, in this case, 6 data points. So I will use this to draw that the data we feed them is actually 6 of them. So they just maybe draw this one. So this is 3. We feed 6 of this, and we get prediction whether these are whether it's real or not. And then we have this sigmoid function that will take this output and give us the probability value between 0 and 1. So that's what the sigmoid function is for. And just annotate this one more time. So 3 are fed to generator, but 6 are fed to discriminator. Okay. And so if we would like to think about that, this is a probability of, is it real? And 1 meaning that it's real, and 0 means it's not real. Let's think about the generator and discriminator. What would be the target probability value for that? Let's just think about discriminator first. The discriminator's job is to discriminate fake from real. So this actually, the first 3 are fake. We already knew these are fake. And this is real. So for discriminator, the target is that since I would like to be really good at saying that it's real image for real images, so for it's going to be 1, 1, 1 for the discriminator, but for fake, it's going to be 0, 0. It's not possible. It's 0 chance. The perfect discriminator will be able to say there's a 0 chance these are real images. That's why it's 0. However, for generator, okay, for generator, the objective function, the objective directionality is opposite. Generator wants to be able to generate the kind of images can fool discriminator to say, hey, it's actually real images. And so in terms of generator, we like the output to be 1, but the generator doesn't really care about real images. If you look at this diagram above here, so in no time generator actually sees these real images, so we only have to consider half. In this case, because we're balanced, fake and real, we only look at half of them. So you can already see there's some differences between the way that the objective function should be set up for both. As a review, for target discriminator, it's going to be fake, 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 real, 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 0, 0, 0, 1, 1, 1. For generator, for the fake, each of the fake image you generate, it like the output to be 1, 1, 1. So that is the setups. Okay. So now we cover this very high level walkthrough of a generated adversarial network with a discriminator and also a generator. Let's look at the generator a bit more detailed. Well, instead of just have 3 examples, we'd like to consider a case where 10 examples this time. So we'll start with the noise. Also, instead of 2-dimensional noise, in the earlier example of 2-dimensional noise, I just tried to have 1-dimensional noise for now, for the sake of simplicity. And so for noise is that we're trying to kind of sample in the space that kind of evenly, and then we would like to have this nonlinear transform to map them into a higher dimensional space that tend to be your output. What does it really mean? Let's just follow me along a little bit. You'll see what I meant. So let's start with the random input. So we just kind of evenly distribute across this 1D space, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We'd like to do some kind of transformation that will give me my output. I would like to generate a 2D signal, x1, x2, and going through one linear layer over here, and also a nonlinear activation function ReLU, and want to generate one more linear layer for output to give me 2 dimension. The reason I like to generate a two-dimensional signal is that I want to be able to plot them, and 2D is something I can plot. So now we can actually visualize the whole process between this battle between generator and discriminator. Okay, so that's the reason I have 2D. But for face images, for instance, of course, there's going to be like say 16 by 16 pixels and so on. So much higher dimension. But for this one, just two dimensions. So I can plot them so you can see the inner working of the generator versus discriminator. It's pretty fun to watch. All right, so let's just implement it real quick. I'm gonna type in some real number so I can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it's like sort of just distribute evenly, but in practice probably add some randomness to it. So this first linear layer, so it's going to be maximum location. I select my first matrix to be the weight and bias, and then my second matrix to be this noise plus this augmented one. All right, so now I'll get this, and I have my activation function, which is going to be, I use the mapping function that's convenient because I could then write my lambda function using functional programming. Lambda for each element within that array, I'm going to say max, x, and 0. Okay, so that is the most common interpretation of ReLU. Do I have my parentheses? Yes, I do. Ta-da! So just as a sanity check, my expectation for ReLU function is that the negative value becomes 0, another negative value becomes 0. Since I'm doing the right thing here, this negative value becomes 0, okay? Everything else is the same. 5 still 5, 4 still 4, and so on, okay? And then at the end, we're going to map the 6 higher dimensional space back to 2 dimensions, down to 2 dimensions. Again, so that I can plug them. So I'm going to do a maximum location, select my weight and bias matrix, and then going up here to select the hidden values from previous there, and I get this 2-dimensional location. Okay, and then I actually have this thing to plot it, but I don't know why it's not doing what I want. I want to see a bit more data. Maybe let's just fix it real quick. I see. So the reason is that the data is like this. Okay, just select this. Okay, and how did the other dimension? How do I do this? I think let's just select the data. Okay, and then oh yeah, here I just fixed it. Okay, cool. Now this is what I want to be able to see. Um, so these are the location of this in this 2D space. Remember going back up here, I just a very simple distribution of noise along this 1D space from 1 to 10 evenly divided. But with this transformation, I get to transform into this kind of linear distribution in the 2D space. And then we could just do a little bit what kind of things that we can change. What if we change the bias here? You can see that it kind of move to the left, move back, move to the right. So bias kind of control how these points are being generated and to explore different spaces. If I add another way here, it's to change the shape a little bit. You can see this is kind of the way within the ability of a generator to use these weights and biases to determine how you will map this 1D noise into some kind of higher dimensional distribution in your desired output space. Let's go back to where we are now. Okay, so that's what the behavior generator generate given is set of input to generate another distribution of your output in this higher dimensional space. In this case, 1 to 2. In reality, is maybe 100 noise dimensions to the number of pixels resolution for your face, which is tend to be much higher. Okay, now that we looked at the generator, let's consider discriminator with this case. How does discriminator work? So then the discriminator will take the fake data. We want to feed the discriminator with the fake data and also real data. So now I have the 6 real data. I already put it in, but now I want to have fake data. What I'm gonna do is I'm just gonna copy or actually make a reference to these 2D locations that I just generated. Okay, I select my X 1, and then select the y value will be this one. Okay, hopefully this fixes this. Okay, now fake data and also the real data I feed to the network. So if I go back to play with my generator one more time, I can say I'm going to change my bias to 0. You can see this thing can move to the left. And then this similarly move to the left as well in the way that discriminator is going to as perceived by the discriminator, but except that all the real images not moving. Okay, so this is to tell you that the real images once you fed to the network is constant, not move around. But what's being moved around is every time you update the generator, the things that generated by the generator can move around. That's where you could actually work around. And all right, so this is a visualization of X1, and this is visualization X2. We look at this visualization a couple times up to all those points. So I'm not going to repeat the implementation. And so now we have let's go into the first linear layer of my discriminator network. And so this is implementation is going to be maximum application. You can see that was 3 nodes and also 3 biases. So I'm going to select my input. This time I'm selecting both the fake data and also the real data here. So I implemented the first linear layer and doesn't work. How come? Okay, because I forgot to select my extra 1 over here. So I'm gonna select my extra 1 over here so that I can apply the biases. Now I have the 3 nodes seeing a different sort of distribution of decision where the positive side increasing, also negative side decreasing. But because of the weight and biases, they have a different distribution. And so first one is the first node, and third is the second node. So you can review the equations. It's going to be the take 3 different weights, 1, 2, and bias. Sorry, 2 different weights and bias, and then select the X1, X2 over here from previous input layer. So then we get the 3 different ways to visualize the neurons, 3 neurons in this node. Eventually, we would like to combine them into just one node because for discriminator, the output is binary, just one node. And before we do that, I want to add some nonlinearity by applying the ReLU function, which is already implemented here. So you can compare ReLU before and after. You can see the effect of ReLU where all the negative values are set to 0. All the blue become white. So that's the effect of ReLU. Eventually put them together by combine all these 3 and against metric representation, I will just implement with the metric modification. And then I'll go up here, select my activation, and I get my final output before I apply the final activation. So usually we call this logit. Let's write it down. Maybe I logit. That usually Z is the most common symbol to represent, to denote these logic values. And that's not probability value yet until we apply a sigmoid function to it. Let me just practice implementing sigmoid here. So I select all my Z values, and then the equation is for each X, each Z, maybe use Z here. Each Z is going to be 1 over 1 plus e to the minus Z. Okay, so this is this sigma, and it becomes 0 and 1. Okay, but then the visualization is going to be just take every element above here and to convert map to 1. So you have this green distribution of what the discriminator is actually seeing in the space. So in this space, if you want to judge that how the discriminator is doing, is that all the real images would like it to be covered by these green areas. The green regions are with regions with high probability value. So it's doing actually quite well. It's picking up most of them. The real ones are within this green region, but the fake ones are outside. So in this case, discriminator is doing the pretty decent job. And now if you can imagine, if you're a generator, what do you want to do? So you want to be able to move those fake points toward the green region. So that is the goal. And how to do that? If I just do it manually, I will just go back to generator. I will going to be something like, I'm gonna move to the right. Remember how I can move stuff to the right? I'm going to move my biases here to 1. I'm gonna move to the right, maybe 2. Okay, and then I realize, and I go down here, in this case, see now the generator, okay, I actually doing better if I have a way to calculate how far is each point to the green area, how far is this green point closer to where 1 is. 1 is like ideal location. Currently is over here in from the perspective of discriminator. So in order for a generator to fool this discriminator, you want each of your fake point to be really close to where the discriminator would have think 1, which is like here. And if you turn around and say, imagine you are a discriminator, say, hey, well, all this fake data are coming closer to my green zone. I don't quite like it. So what option do you have? You could retreat your green zone to more to make it smaller or something, right? For instance, what is that amount to say, what if I can change my bias previously? Like move to the 5, say 5, what's going to happen? So I'm shrinking. Basically, if I reducing the biases to 4 from 6, 5, 4, you can see I'm actually retreating the green zone that to make fake, to make the discriminator making itself more able to say, hey, these are negatives, these are fake images because the probabilities are becoming smaller. But there's a trade-off. You realize that, well, what used to be a real images now has a low probability value. So there's a kind of balance you have to trade. In this case, I'm training the discriminator. I'm training the generator, kind of going back and forth, but by just manually manipulating some of these weights and biases myself. In practice, I actually like the machine to do it. One thing you can do is that you can specify this loss function. What if you can describe this whole process using just the right loss function? So telling the network that how close you are to your goal. For generator, how close you are for all this fake data. Let me just use this one to be close to 1. And then for discriminator, you want all this fake data to be close to 0. That's opposite direction. How do we describe that? And so the next session, I'm going to talk about the loss function that will apply in this situation is binary cross entropy loss. And it's pretty obvious in the way that if you understand for discriminator, the end output is actually just binary value across a batch of fake and real images. So binary output. So use binary cross entropy loss. And the equation for binary cross entropy loss, if you found the deep learning class, now here just kind of review because GAN is the computer vision stuff, but then binary cross entropy loss is very typical machine learning subject. So we start with minus to make it loss. And it's going to be, let's say we have discriminator loss. Let me just zoom in more now. So with discriminator loss, I say I have a prediction that's output is P, but also have the target. Let's just say we use Y hat to define that the target, for instance, is 1 or 0. Earlier we talked about this. Okay, so and the equation is that I'm going to have Y hat times the log base E. This is important. And of P, okay, plus 1 minus Y hat log, also base E, 1 minus P. So this is the equation. And then there's an individual, and there's a kind of index I. You should see I as well. So I put all the I in different places, okay? And this I, what does I index over? So I is actually index over the batch. So 1, 2, 3, 4, all the way to, I actually have 16 examples here, okay? And later on in the class, we'll talk about categorical classification. They will index over dimension as well. In this case, dimension is just 1, binary, but with multiple category, we'll just grow this in this direction. So we have another index later. But for now, for a very simple case of binary cross-entropy loss, you have this very commonly seen equation for that. And so for P, I'm going to just copy, let's implement this. P prediction, I'm going to copy from here. This is our prediction. I just make a copy here. Okay, so this is my prediction. And then for my target is that first we start with discriminator. I would like to discriminate all this fake examples, gray crosses and green diamond. So I want to be able to say these are all zeros. And then I want to be able to say these are ones. Okay. And then you look at the distance between the two. So currently the network is saying this 0.79. Is it good? Is it bad? It's bad, right? But here, then it's saying 0.06. Not too bad. And this is bad. This is not too bad. 0.79 is bad. 0.06 is not too bad for these two data points. Okay. And so let's say, because what I want to be write down is loss. And loss is kind of equivalent semantically to distance, not to similarity. Distance, in that we want to minimize distance. Higher is bad, okay? Higher loss, but I want to minimize it. So it's more like distance. So for this, you look at this, 79 to 0, the distance is kind of high, pretty high. This is kind of medium. This is low, 0.23 to 0, not too far. And this is pretty low. Oh, this is a low one. And then if here on the positive examples, 0.77 to 1 is kind of not too high, low. But here, 0.12 to 1 is high, which is bad. So we like to make sure my equation will give me this, that for this loss to operate correctly. So here I'm going to implement this following the equation. So it's going to be just straightforward the implementation of this equation that I wrote down here. So pretty mechanical here. But I would like to just make it easier for me by using maybe I use let, so I can be able to say, hey, this thing is P. This will be P. And that this y hat, this array will be y hat. And I'll be able to write equation using the y hat, using that. Now, and then I'll just define lambda. Actually, no, I don't need lambda here. Well, I basically just write out the equation right now. Minus, first I should have minus term, but I go inside, come on. And then go inside to fill my equation here. Minus, first is, what is this? Y hat. Y hat times log to the E. I'm going to use ln, natural log, in order to implement that. What is this? Going to be my P, okay? And plus 1 minus y hat, parenthesis, times L natural log and 1 minus P, okay? Hopefully they were just right. My too many parentheses? Okay. The first, I forgot to add a name here. This is actually, oh, I actually got the equation wrong. I should define the name first and select it. That's why, like y hat. Okay, too bad. I just embarrassed myself. So this is the right equation. And I don't think I have I probably need another parenthesis here for this to complete. Okay, now I finish it, but realize why is it missing 1? Okay, let me just extend this by 1. So now I have this binary cross entropy value for each individual example in my batch of 16, and then can match that. Is it high? Yeah, 1.56 is actually quite high. It's correct. This is low. This is low. Just get sanity check some of this value. High, and this is low. Okay, this is actually not correct. Okay, so this is 70. Okay, so this side somehow is not correct. Let me just check my equation one more time. Oh, I see. Because I haven't really put in this number. So these are 0, 0, 0. So everything is 0 here. Let's just type it in. 1, 1, 1, 1, 1, 1. Okay, now it works. So this high is 213, and this is low is like 0.26. Okay, so you can see that this is This is pretty close, darn close, 0.26, but it's pretty high, so this is bad. This example is still doing not well for discriminator. And then eventually we just take an average. I will be able to get the average binary cross entropy across my batch. Or we can also do sum. All right, but this time to do average. Now just repeat this one more time. I'm gonna do a lot of copy and paste. So in this case, for generative loss, the definition is kind of mirroring discriminator, except that we have an opposite direction. So my generative loss going to be the prediction value is still the same, okay, but we only have to consider the fake examples. We don't have to consider the real examples. And for target, this is where things get interesting. The target is actually going to be opposite. We like all my generated examples to fool the discriminator to produce output 1. So this is now I'm going to type my 1 over here. So 1, 1, 1, 1, 1, 1. That will be opposite. And so I can actually copy this equation I worked so hard to write here, but I don't need this. I can adjust it, my selection for y hat here. Now I get this opposite direction. And now I will take an average of this. And then to get my average or mean binary cross entropy loss. Okay, so there is a binary cross entropy loss that we're trying to just calculate at the very low level so you can actually see how the math works. Now you might be thinking why we have to make things so complicated. We have sigmoid, we take exponential, and then we also take natural log when we're trying to calculate this loss function. Why do we have to add it, the natural log? Can we just do without it, make the equation simple? But it turns out when you do exponent and also then you take the natural log, and then things just cancel each other out when we're trying to ask ourselves, what is the gradient? What is the loss gradient? What is the gradient of this? If we change the output, if the network output changes, how does the loss change as a result? Okay, so that's why we're gonna show you the loss gradient over here. So we have this logit here, and then still have a prediction and y hat, and then we have this loss. So that's something we did earlier. This is loss. And what if we want to do is like a loss derivative, partial derivative of loss to actually we can look at the logic directly this time, not P, but logit here to make sure that just highlight here. I'm trying to relate this. Actually, what is a better way to do it? Okay, here, just to make sure you are talking about the ratio between these two values. So I have this total loss here. Let me just consider total loss right now instead of average. Let's do a total loss over 16 batch of 16. And then I would like to compute this. It turns out I have this, if you remember from here to Z logit prediction is 1 over 1 plus e to the z's power minus z's power. Okay, and here we have this kind of crazy equation with all these laws, long and kind of stuff, which I'm not gonna repeat. And we have sum over here. And then when we take a partial derivative, the equation becomes this simple. Basically, prediction minus target. If you remember from our previous lecture for autoencoder, we use L2 loss. And we just add this 1 over 2. All of a sudden, we get exactly the same prediction minus target for our loss gradient. Then we are able to start back propagation and gradient descent using this simple equation. Okay, so let's implement this. How do we implement this? It's going to be prediction is my P, and target is my Y hat, and then the minus like this. This is my goal. I'm going to take my prediction. I come over here, select this, and minus Y hat. I select my Y hat. So for generated adversarial network, it just had to figure out the 0 and 1 for generated fake example and real examples. So okay, so this is my gradient. Seems too simple to be true, or too complicated to be believable. So what I'd like to do next is that what if I will go in just to I have prepared this epoch 1, epoch 2. What happened if we let it run one time, for instance, in the next round, what if we have Z prime here, new logic? That is, then we have some kind of changes in the Z here. I can just simulate the change to this logic. If we update the network weight, we're gonna change the logic, but just simulate this. And so now 0, I have exactly the same calculation down here for the cross entropy loss. Let's just sum this up. I didn't sum this. Let's sum this up. And right now, suppose with no change, and I take the difference between the loss prime, L prime, and L. So this select my L prime and minus L. Okay, so 0. There's no change because there's the logic is no change. Okay, so now suppose somehow the logic goes up by some small value. So suppose I go up by 0.01. Okay, what would you expect the loss to change? In other words, what would be the difference? What value can tell us that? The gradient. The gradient is actually 0.27. Okay, so if I did all my calculation correct, I'm going to see 27 right here. If I let the calculation execute. Okay, so let's see whether it works. Okay, I'm a bit nervous, but let's just move to the right. Okay, see 27. Okay, so okay, not too bad. Let's just try another one. So let's pick another one. So here, let's say this 70, this is gradient 73, and currently the z is 1. What if I add 0, 0, 1 to this? So the 1, let's go up a little bit. Previously it's 1, now it's 1.01, and this time the difference is 0.73. Exactly this number. So we use this real calculation to demonstrate that all this crazy partial derivative calculus you learned many years ago actually matters. They simplified to this value. It does actually quite work. If you are convinced that the initial loss gradient will work, and you could, then we'll be able to run this back propagation to update my weights for the generator, also in discriminator, in the very interesting manner that we're gonna show in this next section, which is adversarial training. So I have this set it up that, let me just zoom out a little bit so you can see the overall, let me see what's going on here. Overall thing that they've zoom, let's say 75%, not enough, zoom to 50%. So I have this set up for back propagation and also for adversarial and over 5 different epoch, and then each of them take in turn. So I have these too small to see, but let's just say we train generator here, and then we train discriminator here, and the train generator here, and again train discriminator, and then train generator again. So kind of taking turn. Okay, I think that's it for my template here. And then going down, I have this back propagation all set up that I'm not gonna implement today because I already implemented this last time. So, but I do want to just implement this real quick. Let's just zoom in over here. Okay, so implement the cross entropy loss real quick. So because I think it's a good practice. In this simple case, I just have 3 noises that give me 3 fake examples, also 3 real examples, and then network is 2 to 4 and back to 1. And so in this case, I just want to review. We have generator. What is the generator's target? It's actually 1, 1, 1 for my fake example. How about this? We don't care. Okay. And so 1 minus 0 is 1 minus y is this actually y hat, but I cannot type y hat. Okay. So just add 1, 1, 1. Here's just kind of, I want you to practice specifying target one more time, but the loss is already implemented. I use a slightly different way. And then here for I'm going to type now. I'm not going to write. For discriminators, the target is actually 0. In this case, I do 6 of this, 3 fake and 3 real. And 1 minus y can just be 1 minus here. get this, and then I'll get this my loss function. Now it's 547 and 173. And first step is to train my generator, right? Okay, generator. My goal is that for generator loss over here, I like this value to become smaller. Okay, let's try one more time. This go over here. I like this after I updated this to be smaller. Okay, hopefully it will work. Now, well, just the final ingredient I need to kick off my backpropagation is to calculate my initial loss gradient with respect to logit this time. And then what is the simple equation I told you about? Prediction minus loss. Sorry, prediction minus target. Where is my prediction? It's up here. I only select three of this. Three, okay? And then minus my target. Where's my target? Here. Here, these three. Okay, so this is my initial gradient, and then I have this all this code. You can review this here. All the transpose and here. Actually, that's it. Oh no, actually it back propagated over here. Okay, so you can review the equation. But here, this is what it matters. I got this. The weight. I'm training my generator weight. So this is my loss and weight, partial derivative loss with respect to weight. And then now this is my weight and it's updated. And then the equation is that I would like to update my generative loss over here to get new weight. The equation is that my new weight, W prime, should be W plus the learning rate and what is this? The derivative, the gradient. And can I make a mistake here again? Gradient descent, this is minus, not plus. Now let's just write this out. So my new weight will be my old weight minus my learning rate 0.1 above here. They just select here and times my partial derivative here. But for the shape to match, I'm gonna have to add my transpose so that the shape can match. So that's how I implement this. Ta-da! So I have my updated weights, and I go down here. So how about the discriminator weight? So because I only train generator, my discriminator weight does not change. I can just copy from my previous step. Okay, so there's no change here. And then let's go down because I have all this question down. What do I have here? Oh, here. All right, so now I now have updated my loss function. It's going from what was it before? It was 5.47, but 5.47 is not changing. This is embarrassing. Okay, why is that? Um, let me just review this again. So generator weight. Oh, maybe the learning rate is too high. It's kind of overshoot. Let's just change to 0.01 here. So it should change even because it's even though it shows 1, but it's actually 1 point something. But just maybe just do it right. Just going to add a little decimals to it so I can see it. Does it change? Let's do this. Oops. Okay. Add a little bit. Okay. They're too small to see, but it should have changes here. So loss. Okay. 5.47. Why is it the same? And this must be bug somewhere because I look at it, although it looks like the same. Let me just, okay, let's see. I'm just debugging. So this here, but I suspect, oh, I see. I have a zero learning rate. I selected the wrong thing here. Okay, here, I just fixed this. My alpha. Okay, now it changes. The way it look different. Okay, cool. All right. Live debugging. Okay, almost done. So okay, now it's going down. Yes, I'm happy. 5.47 becomes 4.08. Okay, so generated is happy. The loss is going down, but someone is not happy here. Who is not happy? The discriminator is not happy down here because it is moving to the wrong direction. As you can see, it's actually going down from 1.7. Sorry, it's going up. The loss actually increase as so the loss decreases for generator at the cost of the discriminator loss goes up. Now this discriminator's turn to start backpropagation and gradient descent. How do you do this? Can start with my loss gradient kickoff and the very simple equation. Prediction minus one uh, target. So my prediction is here. So now I need both of them, both real and fake, and minus my target is 0, 0, 0, 1, 1, 1, da, and then should back propagate not too far up because you only have to propagate over here, the generator weights. So now I have this. This is my loss with respect to the discriminator weight. I mean, discriminator weight. And now I could do update my discriminator weights. Hopefully I don't make mistake again. So I'll select my previous weight minus, not plus, minus my learning rate. Make sure I select the right location this time. My learning rate and my transpose of this. Select this. And then I'm going to add right around with transpose. Transpose. Okay, so this is my new weight. Okay, and then coming back up here, how about my generator weight? No change. This time, only updating the discriminator. So we're gonna copy over here. So this is kind of practice to help you gain intuition. If you copy but you update weights, one here. And then, okay, now let's see what changes. So my loss from 4.08 to up now has gone up because this was the discriminator term to update its weight. The loss actually goes down. Okay, and now I can keep repeating this process. I just need a couple more minutes. So this now generate again prediction minus target. Okay, and now have back propagate all the way up to my weight, and then gradient descent minus learning rate times transpose of my this gradient, weight gradient. Okay, now, but for the discriminator, I'm scroll down. Discriminator is going to be the same from the previous learning step. All right, now with that, is it working? It's just I'm gonna scroll to the area. We can see the weight change, the loss change. Okay, this time we actually see a pretty decent drop. Is that we cannot draw anymore. Anyway, here, decent drop here to 0.46 here. Big drop. In fact, my generator is actually improved a ton, but the cost is that my discriminator losses goes way up as well. Okay, so I suspect this big change probably because I have a really high learning rate. So I do 0.01, this here 0.01, slightly smaller learning rate. It goes up, but direction is still the same. Now we have 6 to 5, but 1 to 3 just has a, so I think this is a bit more of a fair trade-off in terms of the decrease in performance of discriminator. Okay, and now I just do one more step. You can bear with me. And it's going to be to kick off my gradient is going to be my prediction, going out to select my prediction, and minus my target to kick off my gradient descent, a back propagation, kick off back propagation, and then I'll propagate up here to the generator side, And because now, wait, am I updating generator? No, I'm actually updating my discriminator over here. So it can moving around, kind of confusing. Here, now I'm going to take my discriminator weight plus minus my learning rate times my transpose of that. If you use my fancy term, Jacobian, but it's really just a matrix of all these gradients. So then this one now I have a new weight. But just now one more step is to copy. Actually, is that already done? Did I already done? Did I make a mistake here? Oh, here. Okay, no longer here. Okay, maybe I didn't. It's already done. Okay, there was a copy of the weight over here, and so now just have one last step to see what is the changes of the weights. Okay, now my discriminator term goes down, but my generator goes up. So just keep repeating this process. Eventually, sort of reach the equilibrium, and then that's when generator is doing a pretty good job generating images to a degree that the discriminator it have hard time to improve itself to differentiate the two. Okay, so it's pretty packed, but I hope you see how generative adversarial network work in action because it was such a seminal work 10 years ago. They paved the foundation of generative AI for images.